So welcome back. So what we did in the last video is I went through logical equivalence. Now in this video, the first thing I want you guys to do is to try this thing out, try to fill out this whole truth table and pause the video and well actually I'll pause the video and I'll come back with all the answers already written down. But what I want you to do is pause the video and try it for yourself to see if you get the same answers as I do. So welcome back, and I hope you've got the same answers that I did. So the first things first is we have our same pattern for P and Q. Now this exclusive OR, well, we already know this from one of the past videos I did, and I hope you remember that for exclusive OR P and Q, you get 0, 1, 1, 0. So that is something that we've learned in the past. P or Q, 0, 0 or 0, 0, 0 or 1, 1, 1 or 0, 1, 1 or 1, 1. That is also something we learned in the past. P and Q, 0, 0, 0, 1. That is also what we learned in the past. Now if we negate P and Q, we just get the opposite of all the components of the truth value. So we get 1, 1, 1, 0. And if we do P or Q and the negation of P and Q, we get 0, 1, 1, 0. So what did this show us? It shows us that with only negation with negation being that little gun symbol that we have, with only negation and an OR, this is all we need to replace the exclusive OR. So this is equivalent to that. These two are logic equivalent. Oh man, that erased it. So these are logical equivalent. So let's just draw the arrow. They are logically equivalent because all the components, the components that make up these statements, they are the same. 0 to 0, 1 to 1, 1 to 1, 0 to 0. So we know that the exclusive OR, well, it can be replaced by negation and an OR. And that was a pretty simple example, and I hope you got that right. So moving on, this is what we're going to do next. We're going to go through what we call DeMorgan's Law. Now, DeMorgan's Law is pretty simple. Let's just go back and all because I have space. So pretty much DeMorgan's Law is simple to expanding. So for example, if we have negative minus bracket a plus b, then you know we can expand this, right? So we can expand this to negative a plus negative b, and I don't know why this isn't working, but let's just, so we can expand this to negative a plus negative b. So this is pretty much, DeMorgan's law is similar to the law of real numbers, to law for real numbers. So DeMorgan's law is similar to that. So DeMorgan law. It's similar to the law of real numbers. So if we go back to that table, and again, I'd like you to take a minute and fill this whole chart out if you could. But I'm just gonna go on and straight out do it. So P and Q 0, 0, 0, 1. Negate that 1, 1, 1, 0. Negation of P 1, 1, 0, 0. Negation of Q 1, 0, 1, 0. Negated P or negated Q, that'll give me 1, 1, 1, 0. P or Q, that'll give me 0, 1, 1, 1. The negation of this is 1, 0, 0, 0. And negated P and negated Q is 1, 0, 0, 0. So these two guys are pretty much a logical equivalent. But here I want to show you DeMorgan's law, and I pretty much don't have enough space here, so I'm gonna just copy all this and move it to the next page. Perfect. So pretty much what we have here is so this is pretty much logic equivalent to that, right? So that's pretty much DeMorgan's law for you. So let me just write that out. So P Q is biconditional or logical equivalent to negated P or negated Q, and these two are also the same. So negated P negated P or Q is logical equivalent to negated P and negated Q. So these two, so these two, I hate how this program works. So these two are DeMorgan's law. DeMorgan's law. So what we did here is pretty much, or this could be like, just think of this negation symbol as a negative sign, and this P and Q as A and B. So what you're pretty much doing is you're taking this negation symbol and you're expanding it within this little formula that we have here. So we take this negated symbol, we times it by P to get negated P. We take this negation symbol and we times it by this and to get or, because if pretty much a negated and equals or, and negated or equals and. So yeah, so negated and gives us an or, so that is where we got this or symbol, and negate Q is where we got our negated Q. So that's biconditional, or why do I keep on saying biconditional? That's logically equivalent. And the same thing here. We take the negated symbol times it by P to get the negated P. Negated or is pretty much equal to an and negated Q just gives us the negated Q. So this is DeMorgan's law. It's pretty simple. You're just expanding things out. And let's go on to what I copied. So the negation of the conjunction of two primitive statements PQ results in the disjunction of their negations, negated P and negated Q. All I mean to say here, or I copied this from my book, so all they meant to say here is, let's move this so I get some more space. All they meant to say there is that negation of P and Q is logically equivalent to negated P or negated Q. So that's the result that we had in the previous page, in this page. So this is that formula. So the negation of the disjunction PQ is logically equivalent to the conjunction of their negation negated P and negated Q. And all they meant to say here is P, negated P or Q is logically equivalent to negated P and negated Q. So pretty much the DeMorgan's law hold for any two arbitrary statements and not just primitive statements. And as you can tell, it's pretty simple to learn and to understand. What you really did is you just filled out the table. You found out which are logic equivalent, and you found out that pretty much this negated P or Q is equivalent to that. This is equivalent to that, and you found out that negated and is pretty much an or, and negated or is pretty much an and it's just that simple. So please rate, comment, subscribe if you haven't already. This is the end of this video. I don't know what we're doing in the next video, but it'll probably be informing, as I'm pretty sure that you'll be learning from a pretty old book, because I don't think discrete mathematics books get updated that often, because I don't think a lot of people like discrete mathematics at first. Well, even though I did kind of well in it, I still don't like it, and this is pretty grueling for me to do. But I think that some people do appreciate these videos that I'm making. But other than that, please rate, comment, subscribe. Like I said, follow us on Twitter, like us on Facebook, and I'll see you guys again next time. Thanks for